Hey everyone, my name is Dinah Chan Morgan, and I'm part of the community team here at DeepLearning.AI. Today we have really special guests to talk to us about direct preference optimization, and really excited to dive in for everything. Just for everyone's information, the session will be recorded and the slides and notebooks will be available after the event. For any questions, please fill out the Slido link. We've dropped it in the chat, and you can vote on the questions you would like answered the most. For today's workshop, we'll focus on the landscape of chatbots, which has dramatically changed in the past year, which has been fueled by advancements of large language models like ChatGPT and Llama. While traditional supervised fine-tuning has dominated the field, recent research highlights the potential of aligning language models with human preferences for increased helpfulness and safety. This workshop delves into direct preference optimization, DPO, a powerful technique used to train Zephyr, the current state-of-the-art for 7B parameter chat models. For all of you attending, you'll gain practical knowledge on fine-tuning LLMs for chat, understanding the theory and application of DPO with Hugging Face tools, and learn key metrics for evaluating chat model performance. For our event partner today is Hugging Face. Hugging Face is an AI company, I'm sure all of you know that, specializing in natural language processing and machine learning, and is known for its open source contributions and collaborative approach to AI research and development. The company is famous for developing the Transformers library, which offers a wide range of pre-trained models and tools for a variety of NLP tasks, making it easier for researchers and developers to implement state-of-the-art AI solutions. Hugging Face also fosters a vibrant community for AI enthusiasts and professionals, providing a platform for sharing models, data sets, and research, which significantly contributes to the advancements of AI technology. So for today, I want to introduce our first speaker. Hey, Lewis.
Hey, everyone. How's it going?
Happy to have you here. Lewis Tunstall is a machine learning engineer at Hugging Face. His work lies at the intersection of the open source and research teams. He's the co-author of the bestseller NLP with Transformers book and has previously built machine learning-powered applications for startups and enterprises in the domains of natural language processing, topological data analysis, and time series. He holds a PhD in theoretical physics, was a 2010 Fulbright Scholar, and has held research positions in Australia, the US, and Switzerland. His current work focuses on building tools and recipes to align language models with human and AI preferences through techniques into reinforcement learning. Happy to have you here, Lewis.
Thank you for having me, Dinah.
Absolutely. And for our second speaker, we have Ed Beeching. Ed has been a research scientist at Hugging Face for the last 2 years, focusing on building open tooling for LLM fine-tuning, implementing state-of-the-art LLM alignment algorithms, and building preference data sets. Ed is the creator of the Open LLM Leaderboard, co-author of Zephyr, and a maintainer of numerous open-source ML libraries. His PhD was focused on deep reinforcement learning approaches for planning and navigation in robotics. His current research is predominantly embodied learning and LLM alignment. We're so happy to have you here today. Are you guys excited to dive in?
Yes, can't wait.
Absolutely.
Well, take it away.
Great, thank you so much. All right, so we're going to talk today about this idea of alignment in LLMs with the specific lens of an algorithm called Direct Preference Optimisation. And so for those of you who are hearing these words for the first time, this was a kind of big breakthrough from a set of Stanford researchers last year who showed that a lot of the complexity that goes into the kind of conventional alignment techniques that were pioneered by OpenAI and Anthropic can actually be addressed in a much simpler and memory efficient way. And as you'll see throughout this talk, there are some sort of technical details that are useful to understand, and we're going to try and do our best to kind of demystify a lot of the sort of mathematics that goes into these types of algorithms, and also show you some practical examples of how you actually train language models using various tools in the Hugging Face ecosystem. So to get started, I thought it's maybe nice to ask ourselves, like, you know, why would we want to align a language model in the first place? And maybe ask a bit of a philosophical question, what is alignment? So I think most people here probably have some familiarity with language models, and you know that the first step when training a language model is a process called pre-training, where you essentially feed a transformer neural network, typically a large amount of data from the internet, and you get the model to basically predict the next token in the sequence given the previous tokens it's seen. And so this ends up being like a very, very powerful kind of autocomplete model, which you can do tricks like few-shot prompting to generate certain answers. But as an autocompleter, if you ask it a question that is something like information seeking, like, you know, is pineapple on pizza a crime? then this base language model will just auto-complete what it thinks are the next most probable words to that. And in this particular example, it might say, well, this is one of many questions that will be answered at the pizza party, because that completion is from some sort of text that it saw during the pre-training. So these base language models, they have their own use, but they typically need some additional tuning in order to be able to be used as chat models. So the second step is typically called supervised fine-tuning. And what you do in this step is you provide the model with a few thousand examples where you've got a user asking a question and either a human written response or some LLM generated response that provides an answer to that question. So in this particular example, maybe the human annotator really hates pineapple on their pizza, and they wrote in the annotations that this is really bad. And so the model, when you ask the question, says, well, yes, adding pineapple on pizza is a crime under the Geneva Convention. And so this SFT model has essentially learned from the kind of fine-tuning data and also from the pre-training data that there are some biases present there, and those biases can kind of be expressed in this particular way. Now, the thing is, you might be a member of a company like Domino's or Pizza Hut, and you actually maybe your customers, they actually do like pineapple on pizza. And so one way you can kind of sort of adjust your language model to encode those kind of preferences from your customers is to essentially provide your language model with a bunch of questions. You can generate a few answers, in this case, maybe yes or no. And then you can get your customers or your human labelers to annotate this. And then this will give you a way of encoding some alternative preferences that are not directly present in the pre-training of the supervised data. And essentially what you're trying to do is you're trying to learn or teach the model how you can model the probability that the kind of preferred response is more likely than the dispreferred one. And if you do this process correctly, you'll end up now adjusting the probabilities that the model will emit an answer that is more aligned with your human preferences typically. So in this case, maybe you say no, adding pineapple is not a crime, it's a matter of personal preference or taste. So the thing to mention here is that alignment, nowadays I think is often associated with things like censorship. So most people who have interacted with ChatGPT at some point get a refusal, as a language model, I can't do X, Y, Z. But it's really a broader concept, which is that as humans, we typically have some preferences. These are things that, are diverse and depend on our culture and upbringing. But those preferences can in principle be modeled through neural networks. And then we can adjust our language models to behave kind of more in accordance with what our end users may want. So before we dive into DPO, I think it's good to sort of show the original approach that OpenAI pioneered. So they called it RLHF, or Reinforcement Learning from Human Feedback. And the basic idea they had was this very similar recipe. You do supervised fine-tuning. In this case, they had humans basically annotating and creating these examples, these high-quality examples of questions and answers. And then they fine-tuned a variety of kind of GPT models on that data. And last year, when sort of ChatGPT had just come out, the open source community didn't really have many high-quality data sets that you could use for supervised fine-tuning. But this has really changed. And so now there are some really good examples. You have one called Open Hermes from Technium, or Dolphin from Eric Hartford. And these are data sets that you can use today to kind of convert any sort of base language model into a chat model. And these models, if you train on these data sets, you'll typically get a very, very good chat model that you can converse with in certain ways. So what OpenAI did next is they said, okay, we've got this chat model. Now we need a way to sort of model the sort of human preferences from annotators. And so the way they did that is they basically took a collection of prompts, they fed it to the chat model, and the chat model generates a variety of answers. And then those answers are rated by labelers from best to worst. So this gives you a kind of ranking of which answers are preferred over the others. And then essentially you train a new type of model called a reward model which essentially learns how to predict, given some response from a model, what is like the kind of score or the preference score associated with what the human labelers gave. And if you do this, you've now got essentially kind of like a regression model that you can use to basically rate any sort of outputs, and then this gives you a way of sort of mapping those human labels into the preferences of the model. So we've got two models. We've got a chat model and a reward model. And just to mention that we have also now many public data sets that can do this. But you've got the chat model and the reward model, and the final step is to somehow combine those two to create a sort of new chat model that has learned how to encode the kind of signal from that reward model. And the way that OpenAI did it, and also Anthropic, has been using reinforcement learning. So the basic idea here is that you provide your chat model with a prompt, you will generate an output, you can then rate or score that output using your reward model, and then you can use that score to basically update the weights of your original chat model to be kind of more aligned or closer in those preferences. And so if your human annotators are rating things in certain ways, that kind of behavior, those preferences will then be essentially encoded into your updated chat model. And the result of this will be something that is like, ChatGPT or Claude from Anthropic. So mathematically, I don't want to make this too scary, but the basic idea is that you're trying to sort of maximize the rewards that the model can get. So you give it all these prompts, you score the outputs, and you want the model to kind of get better at producing outputs that get high rewards. But if you just only use a reward model, it turns out there's a thing called reward hacking, where effectively the chat model can learn that if it outputs certain words or tokens that have very high reward, it can just keep doing this kind of ad nauseum, and you just get a kind of garbage model that will just output, backslashes or, emojis or something, because it turns out that might be something that is rewarded highly. So what OpenAI introduced was an extra term, which they call the KL penalty. And basically what this does is this measures kind of the distance of your original chat model versus the model that you're currently optimizing. And there's a parameter called beta, which kind of controls how closely you want those two models to be next to each other. And if you take these two things together and you optimize it with a reinforcement learning algorithm like PPO, you get something which is typically a very performant and aligned model. Now, there are certain challenges associated with this. The first one is that anyone who's done reinforcement learning knows that this is typically very unstable. There are many hyperparameters you have to tune. And one of our colleagues at Hugging Face called Costa, he's done this heroic effort to kind of re-implement the original RLHF pipeline from OpenAI from scratch. And there were crazy things like, changing one of the parameters in the atom optimizer had a big difference on the outcome. So that's it's a very kind of, let's say, finicky beast to get right. And the other thing that's also kind of a challenge is that you've basically got two models that you have to deal with. So you've got the chat model and the model that you're trying to sort of optimize and become more aligned. And then you've got the reward model as well. So you've got three large language models that you've got to juggle. And, nowadays the compute hardware is getting quite good, but if you want to do anything, at very large scales of 30 billion parameters or more, you're going to need a lot of compute to be able to juggle this. So this makes the whole process quite challenging, both from an engineering perspective, but also from a stability perspective. So the kind of idea behind direct preference optimization is to say, well, maybe we don't need reinforcement learning. And the question is, okay, if we don't use reinforcement learning, what are the alternatives? So the basic observation they made was that instead of trying to kind of maximize this combination of a reward model or a signal from a reward model with this kind of KL penalty, the idea was maybe we can just change the kind of objective in a certain way that directly encodes or implicitly models the kind of score that a reward model would learn. So you effectively don't have a reward model anymore. You just have your original language model, but your language model, through the process of this optimization, learns how to model those preferences directly. So just to go through this equation kind of quickly, the basic idea is we're going to take a prompt, and then we're going to have preferences, binary preferences of a good and a bad answer. So in this case, you might have your prompt is like, is pineapple on pizza a crime? And then the good response is no, the bad response is yes. And then what we're going to do is we're going to basically compute two things. We're going to try and compute basically the kind of log probabilities that the model is able to kind of correctly predict the chosen response. So here what we do is we take a ratio of two terms. The term on the top is the model that we're optimizing kind of throughout the optimization process. And then we have a reference model underneath it, which kind of normalizes the probabilities so that we don't drift too far away from our reference in the same way that this KL penalty worked previously. And then we have another term which is very similar, but now instead of trying to compute the log probabilities of predicting the desired response, we try to predict the log probabilities of the sort of undesired response. And so if you just take these two terms and you combine them together, you're basically looking at trying to kind of maximize essentially the difference of two terms where one is like the chosen response, one is the rejected response, and you're trying to make the model get much, much better at predicting the chosen response, which should hopefully then align with your human preferences. And the cool thing about this algorithm is that it's differentiable, which means that we can just use backpropagation to optimize the model. And this is also why we don't need reinforcement learning, because the previous objective that we showed before isn't differentiable. So just to walk through the algorithm, you basically take your prompt, you have these two responses of good and bad. You feed them through two models. You have your reference model and the model that you're optimizing, and then you do backprop, and then that's basically it. And in terms of PyTorch code, you can see here that it's, you know, roughly, I don't know, 10 lines of code. So this when I kind of first saw this was like first surprising that something so simple would work. But when we actually tested it ourselves, we found that compared to our reinforcement learning pipeline, it was much, much faster to get models that would converge and be much better aligned than previously. So just to sort of linger a little bit on sort of maybe the most important kind of idea here, there's basically this kind of parameter called beta, and this is the main hyperparameter that you need to kind of tune when you're doing DPO. And Ed will tell us a little bit later about some other parameters that we found are important. But essentially, when we are computing like an update or a gradient update, this is essentially when we're trying to take a direction in the optimization of the model. There's effectively kind of like three terms at play here. So the first term is essentially there's a kind of weighting factor that goes over the loss. And this weighting factor is basically measuring the difference between the kind of reward or the implicit reward of getting the incorrect response versus the correct one. And so if your model is like continually getting like the kind of incorrect answer, or is continually predicting the incorrect label, then this weighting factor will become large because it's a sigmoid, so it will go up towards 1. And then that will kind of penalize the model to basically have a higher penalty for getting the incorrect estimates. And then you've got these other two terms, which are essentially the difference of just increasing the likelihood that your model predicts the kind of chosen answer, and you're trying to decrease the likelihood of the rejected answer. And you've got there's a plot here I've shown of some training runs where you can see that effectively what happens as we increase the beta parameter is we're effectively kind of pushing the model to kind of trains in such a way that the difference between the chosen and the rejected answers becomes larger and larger. And so this can be important because you may have like quite noisy data that has like, you know, kind of fuzzy labels between chosen and rejected. You know, maybe the quality of them is a bit mixed. And by tuning this beta parameter, you can kind of control how much you want the model to focus on the chosen responses versus the rejected ones. And, you know, typically that you have to run a couple of experiments at different values to try and find which is the best one. But the basic idea is that beta fundamentally controls the kind of target margin, which is the difference of these kind of chosen and rejected rewards. And by kind of increasing that, you can get, you know, quite different behavior. And, you know, if math isn't your thing, then Tom Goldstein, who's a kind of grandmaster of memes, he showed this is roughly what's going on in DPO. Basically, you just kind of do gradient descent on the good stuff and you do gradient descent on the bad stuff. And this is why, to some extent, DPO has been so popular, because it's a very simple algorithm, and it means you can basically train models without actually having to train the reward model independently, because you're modeling everything implicitly. So here's a couple of examples I'll walk through. So one of the ones we trained at Hugging Face, it's called Zephyr. And what we were interested in looking at with Zephyr is that in the DPO paper, the authors had explored comparisons of DPO and PPO using kind of small models, so small being like around 2 to 3 billion parameters. And they had done it using kind of like academic data sets. And in particular, they had used a data set for chat that wasn't really optimized for performance. So the idea that we thought was like, well, we know there's this trend in the community to kind of create synthetic data sets that are around essentially using, ChatGPT models conversing with each other or rating each other's responses. If we use those data sets together with DPO, maybe we can get rid of human feedback kind of altogether and still produce a good performing model. And so in this example, what we did is we took a popular data set for supervised fine tuning called UltraChat, and we used that to train a chat model, the initial SFT model. And then we took another data set of synthetic feedback where you essentially have GPT-4 rating responses across a diverse number of different models. And then we use those two data sets to basically do DPO using the Mistral 7B base model, which had only just come out a week or two before. And kind of one of the surprising things we found is that if you apply this process, you get a kind of 7B model that is like, relatively competitive on, various chat benchmarks like MTBench compared to much larger models like Llama 72B. Now, the usual caveat here is that these benchmarks, they have certain biases. So for example, if you train models on GPT-4 data, because GPT-4 is acting as the evaluator, it tends to kind of favor its own kind of style. But nevertheless, if you actually converse with a Zephyr model, it's actually quite capable. And so this was one of the sort of first public demonstrations that you can apply this recipe to larger models with kind of more capable data sets. And since then, the community has really taken this idea and pushed it in much further directions. So, for example, some folks at Argilla, they did DPO on top of the Mistral model, or the Mixtral model, sorry, when it came out. There's a guy called John Durbin who creates lots of very, very interesting DPO data sets, and he used this to fine-tune the Yi34B model. And then, of course, Mistral have been using DPO a lot to align their models. And now Noose Research and Technium have been doing this themselves. So there's essentially, I would say, DPO has become nowadays the kind of canonical alignment algorithm, at least in the open source community. And there's two main libraries that you can use to do this. So the one we have at Hugging Face is called TRL, or Transformer Reinforcement Learning. But there's also Axolotl, which is very popular alternative. And Ed will show you later a little bit about how TRL works. So just to sort of wrap up this kind of quick overview, generally speaking, what you see in like the academic literature in machine learning is once there's a very popular idea, many people try to find ways to extend it and improve it. And DPO is no exception. And one of the sort of first improvements that was made was by researchers at DeepMind. They developed something called IPO, or Identity Preference Optimization. And the kind of observation they made was that when you do DPO, there's a risk that you end up overfitting basically to the chosen response in your data set. And so if you want to prevent that from happening, you can add a regularization term in a similar way that we would do this if we're doing any kind of like regression. You basically add a weight. And they showed in their paper that this gave better results than DPO. And we at Hugging Face also did some experiments kind of comparing the two methods, and we see that they're roughly comparable. There's a bit of trade-off depending on the parameters. And then at the other level, there's a lot of recent work going on around this idea of like iterative DPO. or let's say online DPO. And there's a nice example from Snorkel where essentially what they did was they took a reward model from LLM.AI, and they used essentially the prompts from Ultra Feedback to generate responses from their chat model. They used the reward model to basically rate and rank those prompts, and then they retrain another DPO model, and then they generate again on new prompts, rate and rank. And then you do this a set of times, and you get a model that gets progressively better and better. And what's exciting about this is it's very close to how Llama 2 was trained. Llama 2 was trained in a sequence of progressively improved models. And it's also what we, as far as we understand, is how some of the Anthropic models are trained. They're trained in this kind of online fashion where you're continually improving the model with new data. So I think this is quite an exciting direction. And one of the sort of other more interesting branches that we've seen is a new algorithm called KTO, or Kahneman-Tversky optimization. And this is from researchers at Stanford and Contextual AI, where they make the important point that if you want to collect preference data, you need to have essentially a prompt and two answers, where one answer is the desired one and the other one is kind of the counterfactual, or the one that you don't want. And if you try to do this with human feedback, it's very expensive to collect, because you need annotators to interact with your chat model and pick at every step what is the preferred response. But you can actually, if you're clever like they are, you can actually define the loss in such a way that you only need to collect basically something that is deemed as good and something that is deemed as bad, and they don't have to be related to the same prompt. And so at Hugging Face, we're quite excited about this algorithm. We think it has a lot of promise, and it's probably going to be the thing that you can hope to see from us soon, showing how it works at various scales. The paper itself is worth reading. They do a lot of great experiments, and what seems to be missing currently is having some kind of good label data sets to run this at scale. But this is very, very exciting. So maybe it's a good time to take some questions, Ed.
Yes, absolutely. So let's start off with the first one. I'm just gonna, how do you evaluate the quality of open source alignment data sets?
Yeah, that's a really good question. I would say in general, it requires a bit of what we would call vibes testing. So you just have to look at the data yourself. And I think this is often one of the things that I always try to sort of tell people is like, look at the data, because there's often strange errors in the labels. And probably the most popular method today is to use another language model to do the ratings. So probably the most common example is using GPT-4 to basically judge the quality of responses. And what typically we find is GPT-4 is quite good on many kind of, let's say, creative tasks, or tasks that require maybe like high school level reasoning. But if you ask it to kind of judge the quality of like responses involving maybe some mathematics or some code, it can kind of hallucinate and make errors in judgment. And so this isn't to say GPT was bad, it's just that like any sort of hard task, even for humans, it would be hard to come up with the right answer. But currently today, this seems to be the way that the community is rating quality.
Absolutely. For this question, how much data is ideal for this process, for the alignment?
Yeah, great question. So what we've seen in practice is if you're doing this kind of multi-stage process of SFT and then DPO, you probably can get by with 10 to 100,000 examples of SFT training data, and then maybe around 50K examples for the DPO step. But I have seen examples lately. There's an algorithm called Data, where they show that they can actually use only 6,000 examples for the SFT step, which radically reduces it. So I would say roughly 10,000 examples for SFT and maybe 10 to 20 for DPO. That would probably get you a pretty good model. The open question is that, as far as we know, like the other labs like OpenAI and Anthropic, they're using many more examples. And presumably, if you do this kind of iteratively, you get much better models.
Absolutely. Perfect. Well, thank you so much, Lewis. I think we'll dive into the second section with Ed. So I'll bring you guys up. Take it away, Ed.
Great, thanks. So this is going to be a more sort of practical dive into how to actually run SFT on DPO on your dialogue data sets. One of those things is you have these data sets of conversations, and how do you actually format these in order to tokenize them and feed them to a model in order to fine tune? We've got some links in this presentation to a bunch of SFT and DPO data sets. So if you're interested in getting started, there's a good starting point. And then I'll go through some metrics, mainly for the DPO step of how to sort of evaluate whether your DPO is training well, how to identify problems with your training. And then once you've actually trained your chatbot, you probably want to evaluate it. You might test it out yourself by chatting with it, but you might want some automated way to do that. And so I'll suggest some ways of how we do this and some tools that are available in the community for doing this. Before I get onto DPO, however, I'll first talk about the supervised fine-tuning, the SFT step, because it's important to do this step before DPO. We've actually run some experiments where you kind of skip this step and you jump directly to DPO, and actually it's very, very hard to perform the DPO step. We find that the model, the LLM, fails to learn the dialogue template is one thing that we observe. Right, so I'll get started. Yeah, so to accompany this presentation, we've created two annotated notebooks for SFT and DPO. These have been written in a way that they'll run on a Google Colab GPU, so they should run. Initially, I was thinking we could actually go through this live, but actually these models take many hours to train, so it's better to sort of run them offline. We don't plan to update these notebooks, so we actually have a more up-to-date version of our examples, which is the Hugging Face Alignment Handbook. And so check that out. And this has examples where, if you're like GPU poor, if you've got a consumer GPU with like 24 gig of RAM, you can run some low resource examples with LoRa. And if you're GPU rich, there's multi-GPU, multi-node examples where we do distributed training with Accelerate and DeepSpeed. And in this alignment handbook, we provide configurations, high parameters, scripts for running these examples. I should mention that the notebooks we provide use LoRa, which is a technique for fine-tuning on like low GPU memory GPUs. And I won't really get into LoRa, but I put some links there that sort of talk about it if you want to find out more. And so, of course, the first step when you want to go and perform SFT is to find a data set. So this is the data set we actually use to fine-tune Zephyr. And so it's the UltraChat, a subset of the UltraChat data set. And this data set contains like two main keys that are of interest: prompts and messages. And so just to give an example of what the prompts look like, they might be questions like, what famous landmarks should I visit in London? Write a program in C++, or create a YouTube tutorial on how to make a cake. And it includes the responses, and they might be multi-turn or single-turn responses to these prompts. And the question is, so if you're interested in data sets, we share like a repository of maybe 30 SFT data sets. So go and have a look at them, have a look at their dataset cards, and check out if they're suitable for the task you're interested in doing. And so that should be a good place to get started if you're interested in starting to build a chatbot. And so when you've got these messages in this data set, you actually need to format them in a way that you can give them to a model to perform your fine tuning. And so in order to do this, use something called a chat template. And there are a number of different chat templates. And so the idea of a chat template is like you have a sequence of messages. So in this case, they're math questions, like it's a sequence of math questions that have been asked to a chatbot. And you need to format these in a way that you can like feed them to the model. And so the idea of a chat template is you kind of delineate different sections of these messages with different tokens and different things. So for example, you have a system prompt. In green here, you have like, okay, this part of the message is from the user. And then in blue here, you say, okay, this part is from the assistant, and so on and so forth. I should mention this system prompt at the top here is just blank in this setting. But in some settings, you might want to give your chatbot like a personality, some context of how it behaves, where we have some examples on the hub of chatbots that behave like pirates, for example, or you might have, I don't know, you might want a math-based chatbot, and you could say, okay, you're a math teacher, behave in a sort of math teachery sort of way. So you can give your chatbot some personality, and it might be that your data sets might actually be annotated with these system prompts, and sometimes that can be useful when you're training the model to give it a bit more context about why the model's responses are behaving in a certain way. There are, as I mentioned, there's a number of templates. If you had to choose one, we recommend the ChatML one. It's the sort of most suitable one in our opinion. And then to apply a chat template is very, very simple in the Transformers library. So recently, maybe 2 months ago, we added these sort of custom chat templates to tokenizers. And what you can do is you can define like a Ginger string that will template your messages. I don't expect to read all of this, but it's then very easy. You just call tokenizer.apply chat template to your messages, and it will format them in this way, as I showed in the previous slide with assistant user sort of delineations. And then, so once your data is now formatted in the appropriate chat template, it's very easy with TRL. Just load up the SFT trainer in TRL. Load, for example, in this case, in the notebooks, we load the Mistral 7B model. You can provide some training arguments like the learning rate, the number of epochs, batch sizes, etc. And then you can provide this to the SFT trainer and call trainer.train. And this will take a couple of hours to train your chatbot with this particular dataset. In the alignment handbook, we provide a method to combine different data sets. So if you find a number of data sets that are of interest, you can use those examples there to combine these data sets in a suitable way, so you can train on many different varieties of data. So now you've got your initial SFT chatbot. You want to now perform some sort of alignment to basically to align it to some preferences you might have for your particular product. And in terms of the pipeline, the steps are pretty much the same. So you load a data set, but in this case, there are some additional keys. In addition to the messages and the prompt, you have chosen and rejected. And so this is your kind of human chosen and rejected examples. And again, we provide a number of these data sets. So I think there's maybe 15 examples of preference data sets on the hub there. So again, check that link out if you want to have a starting point. And so, so these data sets, they contain a prompt and they contain a chosen response and a rejected response. And just sort of looking back at the loss that Lewis was mentioning earlier. So the X, the Y, W, and the YL in this case are these kind of tuples that are being extracted from your data set. Not all data sets on the hub actually have this format of just binarized chosen and rejected. Sometimes you can have many responses. So in this case, there are 4 responses to a prompt. And the current DPO implementation in TRL only supports binarized preferences. And so often you find that, okay, the preference of one response is higher than another, and how do these have ratings applied to them? And so what we did in like the case of Zephyr, is that we chose like the highest ranked response and then randomly selected one of the other ones. And we felt that was probably gives a more diverse range of data than, say, always selecting the top 2. You kind of have examples where the margin is larger and smaller, and that provides a more diverse range of training data for the model. You can, of course, have multi-turn examples. So in this case, many datasets have this, and typically it's the last response that differs, so it's either chosen or rejected. There are other data sets, for example, the Open Assistant data set, which is like a big tree of conversations. So you can have many different combinations of chosen and rejected there. There are ways of processing this to do DPO, but it's kind of a bit beyond this talk. And in terms of applying the chat template, these 2 sets of conversations are kind of treated as independent. You tokenize them independently. You do your forward pass through your model, and only when you calculate your loss do you ever actually need to be aware of the fact that these conversations are linked together with chosen and rejected. Applying the chat template is very, very similar to the SFT stage. You just apply it to your chosen messages, your rejected messages, and your prompt. And the DPO trainer will deal with the intricacies of the forward pass of the chosen and the rejected. So when you want to then run your DPO, you can load from TRL the DPO trainer. You can provide the model ID of your SFT model. Again, you can provide a number of training arguments, the learning rate, gradient accumulation steps, number of epochs, batch size, etc. And there's two additional parameters that you provide to the DPO trainer. One is this beta parameter, and this beta parameter, sort of roughly speaking, controls how much you can deviate from the base model. If beta is very high, you penalize deviating from the base model, whereas if beta is very low, you don't penalize it as much. And we recently published a blog post where we compare different beta values and also different loss types. So in DPO, we've implemented, in the DPO trainer, we've implemented the DPO loss, the KTO loss, and IPO. And there's a kind of newer version of KTO that will soon be released that can work in an unpaired preference setting. And yeah, so check out this blog post. It has some examples of these different algorithms with different beta values and their performance. But as Lewis mentioned, if you choose the right hyperparameters, they're kind of comparable in most cases. So I just wanted to sort of highlight some tips when you go and run these algorithms in terms of what the sort of things you should be looking for. And so one is beta itself. And so we typically test from 0.01 to 1. We found that kind of very small values seem to perform well. So if you're going to do a kind of scan, it's probably better to do not just a uniform range, focus a bit more on the lower values. In general, we find that like the learning rate is much, much smaller than the SFT step. Like 5e-7 is what we used, I believe, for the Zephyr model. So it's a very, very small learning rate seems to be the most appropriate. And typically, yeah, when you're doing pre-training or SFT, you try and have the biggest batch size possible that will fit in your GPU memory. And what we found with DPO is there's some sort of trade-off between the global batch size and the number of epochs. So the global batch size is like the batch size across all GPUs. And it's something that you need to take into account. It's not just as trivial as maximizing your batch size to fit in your GPU. Optimizer is an interesting question as well. So in the DPO paper, they were using RMS prop, whereas we found that Adam actually seems to perform better. Scheduler, we found that cosine is better than linear. And a very interesting thing is you can train an SFT model, evaluate it on one of these kind of automated evaluation benchmarks, which I'll mention in a few slides. You take the best SFT model and then perform DPO on a data set. And you don't always get the best DPO model from the best SFT model. Sometimes a worse performing SFT model will produce a better DPO model on the same data set. So it really makes sense to go through your whole pipeline, SFT plus DPO, with your different hyperparameters to really be sure you're getting the best results. And this was a really kind of surprising observation when we saw this. And just to come back to LoRa, we found that some experiments with LoRa appear to regularize the model during training compared to a full fine-tune. And what do I mean by that? So I've actually got an example of plot of a model that we were training. And I apologize, this is a bit pixelated, but I can just sort of briefly introduce it. So on the right here is like the DPO loss during training over 3 epochs on, I think it's the ultra feedback data set. And so in green is the LoRa model that we train, and in pink is the full fine-tune with the same hyperparameters. It's just not using LoRa. And what's interesting is we observe that after the first epoch, the pink loss just kind of shoots down to 0, at least the training part of the loss, whereas conversely, the evaluation loss kind of peaks up. And so clearly, like, we're overfitting to the training data set. Whereas the LoRa model has fewer free parameters, and so it's kind of regularized in a way. And because it has fewer free parameters, you can't overfit as much to the training data set, and your evaluation loss continues to decrease, or at least plateaus. And we see the same thing on the left here. I show the accuracy of DPO. Because your model can be used to predict a reward for a chosen and rejected example, you can calculate an accuracy on each example, or the number of examples in the batch. And we see the same effect, that your full fine-tuning in sort of pink overfits very quickly after the first epoch, whereas this regularization with LoRa doesn't see this problem. And this actually translates to a better performance in empty bench, which we thought was really interesting. It's not just these plots that demonstrate this. To talk about a bit about the metrics that you look at during DPO training. So one is the accuracy. As I mentioned, you can predict the reward for your chosen and rejected example in your batches. And then you can look at the number of times your reward for your chosen is greater than your reward for your rejected, and calculate the accuracy. And so you see here for like a good normal training, your accuracy goes up to like 82% on the evaluation set, which is kind of reasonable. It's kind of what we see across many different training cases. You can also look at the rewards in your batch during training. And while the rewards are interesting, like the rewards for your chosen should be higher than the rewards for your rejected, which is the bottom right. What you're really interested in the margin, so the difference between the two. And so the margin should be increasing during training. It should be that identifying that the chosen have higher rewards than the rejected in a batch. And so this is what you see here. And you see like the blue is the evaluation data set. And we see that these margins go up during training. And of course, not everything will go well during your DPO training. You'll have some runs that don't work, and it's important to look at reasons why. And so in this case, like, it's not entirely obvious from these metrics what is going wrong here. And so you see that kind of your accuracy goes up, plateaus, and then decreases, which is a bit unusual. The chosen rewards plateau and go down. The rejected rewards plateau and go down, which might be okay. They're rejected, so they should be going down. And your margins kind of are above zero, but only just, and they're quite sort of noisy. And so this run, there's clearly something wrong with this run, or there appears to be something wrong, but we weren't sure what. And so it's really important just to go back and look at the loss. And so here it's really obvious, like the loss is super high, it's really spiky. And it turns out in this case, the learning rate is just far too high. And it was probably related to how we use the scheduler. So we train here for 3 epochs, and maybe our initial learning rate was too high. And if it was 1 epoch, it would decay quick enough to resolve this problem. But because we were training for 3, it's high for a long time. And so you kind of overstep when you're optimizing and get these spikes. So if you see issues like this, just lower the learning rate. It's kind of a classic issue in supervised learning as well. Yeah, so you've trained your chatbot, you've found some high parameters that kind of work, your loss goes down, etc. And then you want to go and actually evaluate it in a chat setting. And there are a number of ways to do this. And so the 2 that we look at internally are empty bench, which is like a multi-turn dialogue data set, which tests things like reasoning, math, other examples like summarization, creativity, and there's a bunch of examples in that code as well. And it gives a score basically between 0 and 10. And you see like the most state-of-the-art models like GPT-4 are pretty good on this benchmark. They get like 9.4, so they're extremely good. I should note that internally the empty bench evaluation tool uses GPT-4 to evaluate and judge how good a model is. And we actually have seen some examples, particularly in code and math, where GPT-4, the model will provide the right answer, the model you're evaluating, and GPT-4 will actually say it's wrong. So we're getting to the point now in some cases where you get models that are actually kind of producing a better result than GPT-4, which is quite interesting. It's not obviously on average, it's not the case, but there are some examples where we see this. And here, yeah, we see a bunch of models kind of plotted with their empty bench score. And the second benchmark we look at is Alpaca eval. Basically that rates your model against GPT-4 Turbo. And so the best model in this case is GPT-4 Turbo, which would get 50 basically, because it's just doing as well as itself. And we're seeing like the win rate now for like the Qwen models is like 27, which is pretty good. It's a bit strange, this plot, because the y-axis is non-linear. It's like a log scale. So even this actually looks closer than it actually is. So it's only kind of just over halfway there, but certainly getting there. And the speed at which these models are approaching the quality of GPT-4 is quite astounding. So I think we released Zephyr like in September of last year, something like that. And we were down at, I don't know, at 7.3 and, I don't know, 15%, 10%. And now we're far, far closer to the GPT-4 level. So it's really kind of great that the community is building these models. There are a few other benchmarks that I should mention. And so obviously the best evaluation you want to do is human evaluation. If you can afford to do human evaluation, that's what you're doing. When you've got your final model and you're sure you know internally it's good, you should go and have humans actually evaluate it and make sure you're happy with it in terms of alignment and also the quality of the model's responses. And there's also a few other benchmarks. So there's the Open LLM leaderboard. You can use this to evaluate a chatbot, and there certainly are chatbots that are up there, but it's not really a chatbot focused leaderboard. There's a lot of questions about leakage now, where people, whether they mean to or not, will use a data set which contains some questions from the leaderboard. And there's also questions about overfitting to the leaderboard. So this tool, I think with time will get less and less useful. But it certainly is relevant for the moment. As I mentioned, there's some links here to Empty Bench and Alpaca eval and how to actually use these evaluation tools. There's Llama Index, which is more about retrieval. And so if you're interested in retrieval, this is a very good tool for evaluating models. And there's also this chatbot arena by LMSys. And so I think if you want to actually have a model evaluated on this, you have to ask LMSys to add it to their pool of models. But it's certainly a good model tool to use to evaluate your model. There's this other plot. I linked to a tweet here up the top there of the authors of this. And this is a really useful tool to kind of compare different benchmarks. And so here you kind of see the correlation between different benchmarks. And so this kind of be really useful. So for example, the top one is like the top left is human evaluation. So you see like Empty Bench has like 0.9 correlation with human evaluation. So it shows that it's quite a good tool if you're, as quite a good proxy for human evaluation. Yeah, and there's a bunch of other different metrics and tools in this plot. I think that's it from me. I'd be happy to answer any questions if there are any.
Amazing. Okay, let's dive in. There are definitely quite a few questions to get into. Perfect. So how have you used DPO or seen the successful applications of DPO to optimize metrics in image generation diffusion models such as LPIPs, ArcFace, LOS, etc.?
So this isn't really my domain of expertise, but I know in TRL we have like a DPO trainer, which is for applying DPO to diffusion models. Maybe you can say a few more words on that, Lewis.
No, I think I know that the creator, one of the authors of DPO, Rafailov, he published a paper just recently using DPO to create really good like image generation, and I believe that implementation is currently in the works. So there should be code and models coming this year.
Perfect. How do you know if you should create your own data sets for DPO alignment versus open source?
I think my opinion on this, it really depends on your product or your application. And so you might have a very specific application, like for example, a call center. I could think of that being a really useful place for having a chatbot. to either help someone who's on the call or to use as like, might have a text-to-speech model that's working with the client. And in that case, you might want to have a specific alignment data set for that use case. But yeah, obviously it really depends on your domain of application. There are a bunch of data sets out there, and there'll be more and more coming in the future. And we're also seeing a lot of synthetic data sets being generated. So where researchers use GPT-4 or these other models like Gemini to create synthetic responses to prompts. And you might be able to use this for your application as well. So you might not need to go and ask a human to help make this data set.
Perfect. Are there any open implementations of a self-learning reward LLMs like Meta and NYU research, specifically surrounding self-rewarding language models?
Yeah, so we read this paper. It's a really interesting paper that we're doing some work internally around this. So as soon as we have something, we'll either add it to the handbook or to TRL when we have something. But yeah, it's super interesting. Yeah.
Absolutely. Okay, I think the last question for now, any thoughts on how scaling model size will impact DPO versus RL debate? Noted in paper, they only did DPO with 7 billion parameters.
So this is a good question, and we were wondering this ourselves. And then there was the Tulu model, which was released shortly after, and that was like a 70 billion parameter model, so like 10 times larger. So the size, I think it's a Llama model, or so it's large. It seems to work at scale. There was a lot of question about whether this stuff works at scale, and I would say it's much easier to get DPO working at scale than RL. Yeah.
Maybe just to add a point there. So there are valid applications where using reinforcement learning makes a lot of sense. So the most obvious one is if you want some like in the loop feedback to the thing that you're optimizing. So a good example is that if I want to train a really, really good code assistant, I want the assistant to be able to debug code in a very similar way to like how ChatGPT does. And that debugging can be done by having a kind of environment, like a code environment, where you provide prompts, it generates code, it runs the code actually on an interpreter, and then it gets feedback from the stack trace. And that's a great example where reinforcement learning can really help the model get better at producing correct answers for code that will compile and run. And that would be kind of hard to do with DPO because DPO is typically offline. You generate all your preference data in one go, and then you train on it.
Perfect. Great. Well, I think that's all the time that we have today for questions. Thank you so much, Lewis and Ed. This has been a great session. I know our community has really much enjoyed it. We will send out the slides and the notebooks after the event. They should be in the YouTube video description. And yeah, we'll see you guys next time. Thanks, everyone. Bye.
Thanks, everyone. Bye.